Okay, so recording is in progress, and I'm connecting my Okio cam. All right. Now let me go to the book, and again, hopefully everybody, I'm sharing the screen for the book. Hopefully you can see this. All right. Again, if you cannot see it, please let me know. So let's take a look at exercise number 39. Now, as I'm reading, I'm gonna jot it down on my notepad here so I have it. Now, in exercise number 30, number 39, the question reads, find the values of x, y, and lambda. That's Greek letter lambda. That satisfy the system of equations. Such systems arise in certain problems of calculus, and lambda is called the Lagrange multiplier. Okay, so that's just kind of a background of this a little bit. Now, exercise number 39. So let me actually write this thing down. Okay. So number 39. Let me, I'm going to write the system down. So this is exercise section. I'll show you in a moment what I'm writing on my paper. I'm doing section 1.3, and this is number 39. Okay, so the system is 2x plus lambda equals 0. The second equation, 2y, section 1.3, 39. Okay, 2x plus lambda equals 0. 2y plus lambda equals 0. X plus y minus 4 equals 0. Okay. So now let me change my share to there you go. And, so hopefully everyone again can see my what you call it, my OkioCam recorder here. Okay. So how are we gonna do this? What is it that we need to do? We need to solve the system, right? So let's write this system first in its matrix form. The matrix form of this, remember the coefficient on x, that's the first column. So it's going to be 2. The coefficient on y, that would be our second column. And the first equation is 0. So I'm going to put 0. The coefficient on lambda, that would be like our third variable. It's going to be 1. Because just lambda means 1 lambda equals 0. So this would be the augmented matrix. Now the second equation, there is no x, so the x is 0, y is 2, and lambda, again, the coefficient on lambda is 1, and that equals 0. And finally, the last equation, notice there's no lambda here. So for this one, it's going to be 1, 1, 0, and what is the constant going to be? Is it going to be -4?
Yeah,
Would
it's
it
going to be
be?
-4. I mean, positive
I
4.
think 4, yeah.
It would be 4, right? Because the constant, you move it to the other side. Remember, for the augmented matrix, you got to have like this. You pretty much, you separate the variables in here, and then you separate the constants by themselves to the right of the equal sign. So you got equals 0, move -4, because that's not the coefficient on any variable. That's just a constant. So we do move it to the other side, and it's going to be 4. So there you have that one. right? Next, we just have to do Gauss-Jordan on this one. So following Gauss-Jordan, and I'm going to feed this. Remember, we don't have to do this by hand anymore. I'm going to feed this into Symbolab, and I'll show you in a moment. I'll share that with you. So let's go G hyphen J. That means following Gauss-Jordan. Let's see what this matrix is going to look like. And then we're going to have the solution. So for this one now, let me change my share. Stop share and change it now to Symbolab. Okay. So here's Symbolab ready to be used. And I'm going to, let's see, linear algebra. I have that already. And here's Gauss-Jordan. And we have a, let's see, the size of the matrix, the order of the matrix. This is a 3 by 4, right? Our matrix is 3 by 4. And there's already a 3 by 4 here. You see that one right up here I'm clicking on? If not, you can always go here and choose the size of the matrix. So here's my 3 by 4 ready-made, ready to go. Now I'm going to feed the numbers that I had on my notepad. So it's going to be what? Those numbers are 2, tab, 0, tab, 1, tab, 0. And in the second row, it's going to be 0, 2, 1, 0. And remember, please feel free to interrupt, whatever. If you have questions, if I go too fast, please let me know. All right, and there we have it. So everyone okay on the matrix? We just entered the matrix here. And all I need to do, let me close this one. And then I'm going to hit go. And once you do, and there you go, the solution is right there. This is the Gauss-Jordan. Now I'm just going to copy this matrix. So I'm writing it down on my paper. And then I switch to my notepad. 0, 0, 1, and then I have 2, 2, negative 4. Okay, first, everyone, again, I assume you're okay unless you ask me if you don't follow the steps. Let me go back to share my screen. Stop share, share OQCam. All right, so there we are. And right in here, I just copied the information from Symbolab. Now notice the matrix is in Gauss-Jordan form. That means you have this nice diagonal of 1s, and then you have the nice triangular formation of 0 directly below the 1s, and the triangular formation directly above the 1s here. And if you kind of imagine this hypothetical line there, so we're looking at the coefficients on the variables, call them x, y, and this would be lambda, wouldn't it? Because we have x, y, and lambda for our variables. Usually we have like x, y, z, but again, this is something that in calculus, usually in third semester calculus, the method of Lagrange multipliers for optimization. So something like this could arise at that. Also, they used it in business calculus courses too, the method of Lagrange multipliers. All right, so what does the first row of this matrix tells us? What would be an equation for this first row? Any?
Oh, I'm sorry. Go ahead.
No, go ahead.
Go ahead, Jordan.
Oh, okay. I think it would be just x equals 2.
Perfect. It's 1x, which you're right. We don't write 1x usually, right? We just say x is 2. So I just wrote it this one time. I won't do that anymore. So x is 2. How about the second equation? This one is 1y, right? So that's just y is equal to 2. And
Yeah.
finally, lambda. The last one actually solves for lambda. So right here, 1 lambda is -4, so lambda is -4. And there you have that. So that would be the solution to that system. Everyone okay on this exercise?
I think
Because
there's a question in chat.
Oh, thank you for that, for pointing that out, because I usually don't keep track of that. Let me go here and, oh, thank you. Okay, so in chat, okay, thank you, Ryan. Sorry, I'm always behind in the chat. So, why wasn't the original matrix -4 again? Okay, I'll explain that. Because somebody else answered it. Thank you, Leo. Because you need to add it to the, yeah. Again, the question, why wasn't the original matrix -4 again? The reason, let me switch. Okay. The reason is because all our systems, so I'm just going to write it in general. Let's say I have A x plus B y plus C z equal D. And let's go A1, B1, C1, D1, like that. So that would be our first equation. The second equation is in the form A2x B2y C2z equal D2. And let's say we have 3 equations, 3 unknowns on this one. So it's going to be like this. So there we go. We have these. We have this system. Now, if you note here, to the right, we have these constants. So these are the constants, right? Those are the constants. And here we have the variables. So that's the general structure we are working with. Now, if you look at the original problem in number 39, they got the variable here, that's good. Variable here, that's good. Well, lambda's coefficient is 0, so they didn't write it. But then again, this constant is misplaced. See, by this convention, we got to have our constants on the right side. So that is the reason for the constant. We had to move it to the other side. So to keep it in check with this system, right? So it has the general form of the system here. All right, so I guess everybody's good. Excellent. And thank you again for pointing out to me the chat, because again, I totally lose sight. Because when I share my screen, I can't even see Zoom on my screen. So I have no clue that somebody posted something in chat. All right. So any other questions? So far, I hope everyone's okay in the course with what we've done thus far. Is it safe to say the class is okay with what we've done? Yes.
Yeah.
Right. Fantastic. So let's do that then. Let's begin chapter 2. Now, in chapter 2, let me change my share back to the book share. All right, so I'm looking at chapter 2. In chapter 2, actually, this is a good chapter. Now that we have the preliminary stuff, we know what the linear system looks like. We solved it using Gauss-Jordan. The key is the Gauss-Jordan here. And now we're going to actually do Gauss-Jordan throughout the rest of the course. So it's an important form of a matrix. Now, this evening, we're going to just look at these 3 sections. So let's begin with matrices. Now, I'm gonna, so that's just where we are in the book. And now I can actually start or begin our lecture for the evening. Now, we already defined a matrix, right? We know what a matrix is, a rectangular array of numbers. That's what a matrix is. So what are we doing in this chapter? We're going to see how we can work with these matrices. So for instance, is it possible to add them? Is it possible to subtract them, multiply them, and so forth? Now, the major operations that we do with numbers. So for example, with numbers, we can add, we can subtract, we can multiply, we can divide and all that. The division is not defined with matrices. So just to mention that, there is no operation division with matrices. The closest we can come to a division is to go through the inverse of a matrix. And we do talk about inverse matrices this evening. So keep that in mind. It is possible to add, subtract, and multiply them. So, but before we do that, let's talk about some key ideas here. One would be the equality and the equality of matrices. So here, what we're interested in, what we want to know is that how can two matrices, and I have here, by the way, the word matrix, that's the singular form of the word. When we have two or more matrices, so the plural version of matrix, that becomes a matrices. So that means two or more. Equality of matrices, so two or more matrices, which is inaccurate. Matrices is matrices. So let's say I have matrix A, and we define matrix A to be in the A subscript ij. So that means this matrix is made up of rows and columns. So for example, the first row is A11, and then we go A12, A1, and suppose I have N as in Nancy, N columns, and then so on and so forth, all the way up to the last row. Let's say we have M rows. So this matrix has M rows, N columns.
What's that on the subscript of the first A in the brackets?
This one is subscript ij.
Okay.
I and j. I is subscript we use for the row, and j is subscript that's used to indicate the column. So for instance, if we write A2, 5, something like that, this means the element in the second row and in the fifth column. It just gives you the address. So that would be the row, and that's the column. It looks like 25, but it really has no significance. It's nothing even close, resembles 25. It just really looks like 25, but it's not.
What about if there was like 253? Would it be like row 25 and column 3?
Oh, okay. For this one, because remember, first we define the size of the matrix. So for instance, if my matrix is of size 25 by 10, let's say, how's that? 25 by 10. That means it has 25 rows, 10 columns. So I determine that ahead of time. Now I can interpret the subscript according to what I see here. So would it make sense? Would it make sense to say that this is row 2, column 53?
No.
No, because see, I have 10 columns here. So if I have A sub 253, looks like that means 25th row, because I have 25 rows. So that's row 25 and then column 3. So that's how that would work. You see that?
Yeah.
Okay, sure. So there we have that one. So that's the purpose of the subscript. Now, AM sub 1, and then suppose I have M row second column, so on and so forth. We're going to go to A, M, N. And all this means is that I have a matrix that is M by N, correct? M rows, N columns. So we can write it in expanded form, full matrix form, or we can write it like this. Now, if we just write it in this form, we don't see the elements, do we? I mean, what is A15? I have no idea. In order to see every element, every number in the matrix, we really need to write it in expanded form, full matrix form, so we can see those numbers. So this one on the left is more of a notation. This one, it's more of a notation. We use it for theorems, for properties, so on and so forth. So for example, remember right now we're talking about equality of matrices. So let's talk about that one. Suppose A is this, and then let's say I have a matrix B that I can call it Bij, right? Because I use A for B, I'm going to use a little b for the elements. Now, in order for two matrices to be equal, first, they have to have the same order. Remember, order means size. They have to have the same size. In other words, this has to be m by n, just like A is. So as long as they have the same order or are of the same size, then two matrices A is equal to B if they have the same size. That's like the important prerequisite. They must have the same size. And in addition, this is a conjunction, means both parts must be satisfied. And every element in ij position of A should equal to exact same element in exact same position. Here again, I are the rows. Remember I said we have m rows, these are the rows, and J is the column. So J goes from 1 to n, right? And these are the columns. This would be the condition for equality of two matrices. They gotta have the same size and the elements must be identical. So for example, let's say matrix A is 1, 2, 3, 4. Matrix B is 1, 3. First, what's the size or order of matrix A? Two rows, two columns, right? It's a 2 by 2. And what about B? B is 2 rows, 1 column, right? 2 rows of a single column. So you see how they have different size. Therefore, if I want to do A plus B, this one, undefined. We cannot do A plus B because I don't have corresponding elements to combine with. They don't have the same size. Now, if they have the same size, so for example, let's say I have A, 1, 2, 3, 4, and B, let's say that one is 6, 7, 8, 9. Then if I do A plus B, would I be able to add them now? Looks like I should be, correct? Because this is 2 by 2, that's 2 by 2. Now, what does this equation means? Aij, Bij. That means the element in the first row, first column of A combines with first row, first column of B. So A plus B, that's 1 plus 6. The element in the first row, second column, first row, second column add together. So that's 2 plus 7, then 3 plus 8, and then 4 plus 9. And this is going to be what? 1 plus 6, that's 7, 9, 11, and 13. You see how that works? Now, the matrix addition, by the way, is a commutative. That means if you do A plus B, B plus A would be the same thing. For B plus A, you just combine 6 and 1. Well, it's the same as 1 and 6. For B plus A, you do 7 plus 2. Well, it's the same as 2 plus 7 because addition is commutative. So A plus B in general equals B plus A. Okay. Now, matrix subtraction. What do you think? Do you think matrix subtraction would be commutative? Addition is. How about subtraction? So for example, just think about it in terms of numbers. an example with just numbers. Suppose I have 5 minus 3. Would that equal to 3 minus 5? Doesn't look right, does it? 5 minus 3 is 2. 3 minus 5 is negative 2. They're not the same. So the same thing with matrix. For matrix operations, so A minus B, matrix A minus B doesn't equal matrix B minus A. There is no commutative property of subtraction. And you probably observed, by the way, I didn't mention it, we usually use capital letters for matrices. So we go the first part or the latter part of English alphabets. So we're going to go A, B, C, D like that, or we're going to go X, Y, Z. The A, B, C is fairly common, but again, it could be whatever. We can use the latter part of the alphabets. So everybody good on this one, I hope. Again, please ask, otherwise I'll keep going. So now having talked about that one, let's talk about a column matrix. So what is a column matrix? A column matrix, or a column vector, they also call it. Sorry, I know I'm up here. Move down. Sorry about that. So a column matrix, or it's also known as a column vector. Either or. We'll see later the connection between vectors and matrices. So a column matrix, this is a matrix that has only one column, and hence the name column vector or column matrix. So for example, as a vector, because you've seen vectors before, so as a vector, now this is vector A, I'll put an arrow on top. So this is a vector quantity, right? It is not a matrix, but I can represent this vector, for example, 1, 0, 0, right? This is a vector. Now, this definitely looks like a matrix, doesn't it? So I can say matrix A is equivalent to 1, 0, 0. Now I'm thinking in terms of rows and columns. Matrix, see, I don't have an arrow on capital A. So this is going to be a 3 by 1 matrix. So either or, notice again, we can have a column, you can call it a column matrix, or you can call it a column vector, depending on what it is we want to do with it. So there's a very close tie between matrices and vectors. So that's the column vector. Only one column. Now rows could be whatever. So I can, for instance, I can have column matrix B, and this is going to be 1, 2, 3, negative 1. You see that? So this time I have, this is a 4 by 1 as a matrix. Capital B. As a matrix, this is a 4 by 1 matrix. The 1 here for column is important. It's got to be 1. And then we talk about a row matrix. So what is a row matrix? A row matrix is simply going to be, or we can also call it, or a row vector. Row vector. What do you think a row vector would be if we bounce off of a column vector?
The same thing, but with only it'll be instead of being vertical, horizontal.
You got it. You got it. So this one, a row vector has only one row, and hence a row vector or row column. Yeah, for this one, this time as a vector, vector A could be 0, 1, negative 3. Say I have one row and 3 columns. This would be capital A if I think of it as a matrix. Row vector B, it could be 0, 0, 0, 1, negative 1. You see that? Or that I can think of it as a matrix B. It has one row, 1, 2, 3, 4, 5 columns. Okay. Now, one thing, let me point this out. When we talk about vector quantities or matrices, in the book, let me change my share. I'm going to go back to the book now. Share, let's take a look at the book. In the book, what they do is the following. Right in here, you see how they use boldface right in here? That is the boldface that they use. So for vector quantity, we're going to use boldface. Now I can, it would be kind of a hassle to use boldface. So what I do, and what mostly everyone does in the classrooms or on their notebooks, so we don't have to boldface things, we just put arrow on top. So in the book, again, it's boldface, but I don't use boldface. But let me show you one just so you know what I mean. Let me stop this share and go back to my OQ cam. Okay, so this is what I mean. Here's a vector A. In the book, this is what they do. And you see kind of why it's not feasible for me to do this. That is boldface A. It's not the best A because my paper is kind of warped. Okay, so you see that? This is what I mean. So if it's boldface, that means it is a vector quantity, folks. I just put arrow on that. So this is a vector. Just a notation, an agreement between us. All right, so everyone okay with these definitions, I hope. Now, let's talk about scalar multiplication. Scalar, remember, we're looking at operation with matrices. Scalar multiplication. Okay, now scalar multiplication here is written this way. So I have little c, and then I have this capital A. C here is what we call a scalar. A scalar, the reason it's called a scalar, because this is a real number. C is a real number. That's what C is. Like 2, 5, -5, and so on. The reason it's called scalar because it quote unquote scales the matrix. So for example, and I'll show you in a moment, what do I mean by scaling it? So CA is a scalar. Think of it as a constant multiple of a matrix. So what does CA mean? That means in our funny looking notation, that means C times I sub j. Aij. The constant multiplies by every element of the matrix. Okay, so for example, let's say my matrix A is 1, 2, 3, -1, 0, 5. Right, that's matrix A. And then I'm just making a constant multiple of A. So suppose I want to do 2A. You see that 2 is a scalar. So it's going to scale this matrix, and by scaling it in this case, it's going to double the magnitude of every element, isn't it? It's going to double it. So I need to multiply 2 times every element of this matrix. That's what this says. So I'm going to do 2 times 1, that's 2. 2 times 2, that's 4. 2 times 3, that's 6. 2 times -1 is -2. 2 by 0 is 0, and 2 by 5 is 10. Everyone okay on that one? So that's what scalar multiplication is. It's constant multiplication. So keep in mind, please, you multiply every element of the matrix, not just the row, not just the column, every single one. Now, what about, for instance, if this is A, let's do negative of A. What do you think negative of A is going to look like? If that is A,
-1, -2, -3, and then second row, 1, 0, -5.
perfect. Thank you very much. So I'm just going to write what you just called. You said -1, -2, -3, and then 1, 0, -5. Perfect. Thank you. Now, having defined negative of a matrix, we are in a position to do this. Suppose now I'm going to define matrix B to be a matrix. It's got to be the same size as A, right? It's got to be a 2 by 3. So I'm just thinking of a 2 by 3 made up. So let's go 5, 0, 2, 0, 1, 3. That's my B. I'm randomly making these numbers, folks, not thinking of anything in particular. So there you have, that's matrix B. Now, how would I do matrix B minus A? Notice we're actually doing matrix subtraction now. So to do B minus A, we actually do B plus, we're going to add negative of A to B. Does that make sense? And we kind of do that with everyday numbers too. For instance, sidebar example with numbers. Let's say I have 7 minus 3. Couldn't I think of, this is operation is subtraction, right? I'm subtracting 3 from 7. But I could, if I chose to, if need be, couldn't I think of this as addition? I don't like subtraction. So for me, that's addition, but then I have to adjust the 3, right? Here I'm subtracting 3 from 7. To subtract 3 from 7 is to add opposite of 3 to 7, isn't it? It will give me exact same results, doesn't it? That's 4. This is 4. So this is just rethinking. This is addition. This is subtraction. So pretty much that's what I'm thinking now with the matrix. I'm subtracting. So to subtract is to add with opposite of matrix A. And now we've done matrix A. Opposite of that is this one. So that's simply going to be what? 5, 0, 2, 0, 1, 3. And negative of A. So I'm going to add to this one, C plus these elements, -1, -2, -3, and then 1, 0, -5. And remember earlier we said to add or subtract matrices, you combine elements in the same row column, right? So we're going to do that. So 5 and -1 add together. So the first element's going to be 4. Then we have 0 and -2. Those add together, leaving with -2. And what else? And then we have 2, -3, that's -1. 0, 1 makes 1, 1, 0, 1, 3, -5, -2. And there you go. So it is possible to subtract matrices. So we have addition, subtraction so far. And we just saw example of scalar multiplication. Everyone good, by the way, still? Any questions so far, ladies and gentlemen?
Yeah.
We're good? Okay. All right. Now, having talked about it, let's talk about the next operation is going to be matrix multiplication. Let's talk about matrix multiplication. Remember, just now, earlier, I talked about scalar multiplication, right? Not matrix. So it makes a difference whether I'm multiplying by constant or I'm multiplying by matrix. So we got two types of multiplication. A constant multiple of a matrix, and then we actually have genuine a matrix times a matrix. Now, in order for matrix multiplication to be defined, here's what's going to happen. Matrix A, that's made up of row ij. Okay, suppose this is an m by n, right? Like the one I made earlier about half an hour ago. So suppose I have that matrix. And then I have this other matrix B that's also ij. Now the order of this matrix B cannot be m by n. When you add them, they have to have the same order, right? but not when we multiply them. Now, in order for multiplication to be defined, B has to be n by P. So the catch here, folks, remember, and the size of a matrix is always row by column, isn't it? Row column, row column. So in order for multiplication to be defined, the column of the first matrix, whatever the number of columns, should match the number of rows of the second matrix you want to multiply. This is very important. That's a must. Absolutely, we have to have that. They have to be the same. Now, the size of the product, and in here, I'm assuming I'm doing A times B. The size of the product, let's say that's matrix C. We're going to call that Cij. The size of the product matrix, it's going to be the row of the first matrix by columns of the second matrix. So it's going to be M by P. You see how that works, everyone? So inside numbers should be equal. The outside numbers is the size or order of the product matrix. Otherwise, the product is not defined. Okay, and just for to be complete here, remember, I am assuming I goes from 1 to M, and J is a 1 by N matrix, just to make sure we know what these M and N are. The I and J related to M, N. And remember, P here is whatever the number of columns of this one is. And there you have it. So let's do an example. Any question first on the notation, anyone?
I'm still a little bit confused, but I think it's probably best we work a problem out and maybe go a little bit slow.
Oh, okay, sure. So let's do an example of a multiplication. So in our example, first of all, example. So we are again still in section 2.1. Okay, section 2.1, an example. Let's say, first of all, A is 1201. It's a 2 by 2. B, I'm going to make it 100. It's a column vector, 3 by 1. First of all, I want to do AB. What do you think? Can I do it? Is that multiplication going to be defined?
We can't do it because the column on A is not matching the row on B.
Very good. You see that? These are not equal. So this multiplication is undefined. Means no, sorry, we cannot do it. It's really just that. Now, let's make one that actually works. So let's say A. I'm going to make A to be, let's say, 1, 2, 3, 4, 5, 6. And so this is a 2 by 3. Now I'm going to make up a matrix B. How many rows should B have so I can actually multiply? How many rows? Not columns, but rows of B.
Could be 3.
Perfect. It's got to be 3. So I'm going to think about, remember, this is column of A. It's got to be same as row of B. So I'm preparing 3 rows here. 0, 0, 4, 5, and 1, 2, -1, -2, 1, 1, 1, 3. Would that work? This is a 3 by 4, isn't it? Correct. And now these are equal. So everyone okay with that? So yes, multiplication is defined. Good, we can do this. Now, what will be the size of the product, AB? Just the size, and I show you how to do it.
I think it's AB would be 2, 1.
It's gonna be good. This is gonna be,
Over this one, it would be 2, 4, I think.
you got it, perfect. So the product's gonna have 2 rows and 4 columns, isn't it? So let's prepare for that. Here's a matrix that has 2 rows and it will have 4 columns. So that kind of, again, makes me aware of how much space I need and the size of the matrix. I'm just going to put a 2 by 4. That's what that is. Now, I'm going to put circles here. You don't have to. You're welcome to, but I'm going to redo this matrix. I'm going to write it down below in a moment, but this is going to help you. Okay. 2 by 4. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8 elements, right, in the product. Now, what is the address of this entry? This one. What's the position of that?
Second row, second column.
Good. Isn't that row 2 and row 2, column 2, isn't it? Right? First, second row, first, second column. True? So actually,
Yeah.
the address of these entries, the elements, tell me how to do this. So here's what 2, 2 means. That tells me to multiply the second row of matrix A by second column of matrix B to get a number here. Again, multiply second row by second column. So here's how it goes. Second row, I'm just going to go 4, 5, 6. I'm just singling out these 2. And second column, isn't that 0 to 1? Now here's how the multiplication works, folks. You do 4 times 0 plus. Then you do 5 times 2 plus. Then you do 6 times 1. And add them up. 4 times 0 is 0, correct? 5 times 2 is 10. 6 times 1 is 6. That's 16, isn't it? So the element in that spot, in the second row, second column of the matrix of the product, it's going to be 16. See how that works?
But can you do it one more time, please? How you explained the from 4, 5, 6 to 0 to 1?
Okay. So again, we located this element, right? Everyone agrees that's second row, second column. So we located the element we want. So row 2, what I did, this is matrix A, row 1, row 2. So I brought row 2 down here. And then this means second column. So I brought the second column, this column, in front of it. So everyone, again, you're okay on that step?
Yeah, I'm okay now.
Right,
Thank you.
second row, second column, because of this. Now, to multiply, again, you multiply first element by first, second by second, third by third, and then add them up. So 4, 0 is 0. 5, 2, that's 10. 6 times 1 is 6, so the sum is 16. That's going to be the number in that spot. And don't worry, we get to do this 1, 2, 3, 4, 5, 6, 7 more times. So by then, hopefully, everybody's going to be okay with this. But are we good so far? How I got the 16?
Yeah.
All right. So let's actually now go across the circles and do them in order. What is the position of this entry, this element?
row 1. I mean, yeah,
Yeah.
row 1,
Row 1 and the column.
column 1.
Perfect. So let's bring row 1. 1, 2, 3. And column 1. 0, 1, 1. And then do the same thing. Row 1, column 1. You do 1 times 0, 0. 2 times 1, 2. 3 times 1, 3. And then we go 2 plus 3 is 5. There you have it. So that's going to be the element in the first row, first column. So this was 1, 1, right? This is 1, 1.
Yeah.
How about this one next to it? Row 1.
Column 2.
You got it. So let's write 12. Row 1, column 2. So that means I'm going to copy the row 1, 1, 2, 3, multiply by second column 2, 0 to 1. And once you do this a few times, folks, I mean, this is perfectly normal right now. It's going to take a while. But what we want to do ultimately is this. You really don't want to write these down. Again, it's okay right now because we've never seen this, so that's fine. And the reason is I'm going to have to write this. You're going to have to write what we're writing here 1, 2, 3, 4, 5, 6, 7, 8 times. So hopefully we get to a point, maybe for this last one, we do it without writing the details. But let's still keep it. 1 times 0 is 0, plus 2 by 2, 4, plus 3 by 1, 3. The sum is 7. And there you go, 7. Let's do this one. This element is in first row, third column. Right? First row, third column. So we're doing first row, 1, 2, 3, by first column, 0, 1, 1. Okay. Now for this one, so wouldn't that be 1 times 0? Right? We do in first row, first column. Right? This row by this column. So we do 1 by 0. That's 0. 2 by 1. That's 2. 3 by 1. That's 3. So don't I have 2 plus 3 plus 0? That's 5, isn't it?
Yes.
Is it okay if I write it just 5?
Yeah.
Okay. And again, if you need to, feel free to write them down. But let's see, because otherwise it will take too long. It will take too much space. So it's going to go faster. And Symbolab does, by the way, it does matrix multiplication also. It's just kind of how we want to do it for now, just to learn it. All right, let's do 1, 4. So that means first row. This is first row. There we're doing first row. And we're doing fourth column, aren't we?
Yeah.
Good. So here he goes. Again, I'll do this, and then for the future ones, you guys call it out for me, please. So I'm going to go 1 by 5. That's 5. 2 by negative 2. So that's
-4.
negative 4. 3 by 3.
9.
Perfect. So that's going to be 10, isn't it?
Yeah.
Good. And there you go. Now, can anybody, if you don't mind, could you tell me what the second row first column would be? Let me put my markers for you. We're doing second row now, and that's the first column. Remember, we do elements, each element by element.
Is it 11?
The answer is going to be 11. Very good, Jesus. Is everyone okay? 11 is the answer. Perfect. 4 times 0 is 0. 5 by 1, 5. 6 by 1, 6. So that's 6 plus 5 plus 0, 11. Fantastic. And so we already did 2, 2. Let's do second row, third column now. Second row, third column. Here's second row, and here's the third column. What should the product be?
17.
17. Let's verify. 4 by 4, that's 16. 5 by -1, that's -5. And 6 times 1 is 6. 6 minus 5, that's 1. 1 and 16, very good, 17. Are we okay on that one? Perfect. And let's finish this off. This product, what's the address for that element? Where is it located?
Second row, fourth column.
Thank you. So this would be 2, 4, right? Second row, fourth column. So you see how it helps us, folks? Once you identify the location of that element, it tells you which row and column to use, doesn't it? It says use second row of the first, fourth of the second. This is the second row of the first, fourth column of the second matrix. So what will this end up being?
28.
28, perfect. You got it. And we'll confirm just to make sure. So we're going to go 4 times 5, that's 20. 5 times -2, that's -10. 20 minus 10, so far is 10. And then 3 by 6 is 18. So it's 18 and 10, 28. Perfect. And there is the product. Is everyone okay on matrix multiplication?
Professor,
Yes.
for the element in the first row, third column,
This one.
yeah, I got 6 for that one.
Let's check it. First row, third column. Let's verify. So for this one, first row, third column. Okay. I'm going to keep my markers here. Okay, first row, third column. So you got to do 1 by 4. That's 4. And then it's going to be 2 times -1. Remember, 4 and -2, so that's 2. And then 3 times 1 is 3. So 2 plus 3 is 5. Right? So it's going to be 5.
Got it.
Do we address again what the result is? Do we still address it as second? I mean, that is a 2 by 4. So we still address it first row, second row, and whatever column we're addressing out of the 4.
Correct. Correct. And that is why it's important for the inside to be the same, and then the outside could be whatever. Who cares? It doesn't matter. The first matrix could be 50 by 3. The second one could be 3 by 1,000. So it will be a 50 by 1,000 matrix. As long as the insides are the same, that just gives us the green light to do it. The outside numbers give us the size of the product. Again, 2 rows, 1, 2, 4 columns, 1, 2, 3, 4, and then we label them first row, first column, first, second, first, third, first, fourth. Moving on to the second row, second, first, second, 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 third, second, fourth column. Are we okay on this, everyone? All right. Now, just a note here. In general, matrix multiplication is not commutative. In fact, AB, BA may not be defined. Let's say this example that I just made up, this one, clearly AB was defined, wasn't it? We did it. Let's say I want to do BA with the same two matrices you see. Let's say I want to do BA. What is the size of B? 3 by 4. The size or order of A is 2 by 3. What do you think? Is BA defined?
No.
No. See the inside numbers? So the product is undefined. AB was definitely defined, BA is not. So again, this is something that doesn't hold, which is unlike with numbers. Remember with numbers, 4 times 7 equals 7 times 4, isn't it? So it works with scalars, but not in the world of matrices. It doesn't work. Okay. So if you're good with this one, now next we're going to talk about systems of linear equations. Linear equations. Okay, now with systems of linear equations, this is going to be the general form of a system, algebraic form. And I'm just going to write one with 2 equations, 2 unknowns. We can extend it to higher order systems. So for 2 equations, 2 unknowns, here's my first equation. A11 is the coefficient on x1. A12 coefficient on x2. And let's say that's going to equal the constant B1. The second equation, first, x2, x1, and this is x2, and that's b2. So everyone okay on that? That is my system. This is a system of linear equation, 2 equations, 2 unknowns. Now, it is possible to write this system as such. We can actually write this as a matrix of coefficients A11, A12, A21, and A22, multiplied by a matrix. This is a column vector now. A column matrix means it has 1 column, 2 rows of variables equal to a column matrix of constants. We are allowed to do this. And you can verify, now that we talked about matrix multiplication, this is a 2 by 2, x1, x2, that's a 2 by 1. This is a 2 by 1. So the matrix multiplication is clearly defined, right? And the size of the product is going to be a 2 by 1, right? 2 by 1. So how are we going to multiply this? Just to show you. Remember this element? So I'm getting ready for 2 rows, 1 column. So here's a 2 by 1. So remember how the multiplication goes? This element is in the first row, first column. So I'm going to do a first row by first column. So it will be A11x1 plus A12x2. And there you go. The second row, the product in here, second row, first column. Second row, first column. You do A21 by x1. So that's A21 x1 plus A22 x2. And that's exactly what this is, right? Isn't that A11 x1 plus A12 x2? A21 x1, A22 x2. And this should equal to B1, B2. And earlier we said 2 matrices are equal, equality of matrices, if they have the same size and the elements in that same position are equal. So from equality of 2 matrices, we're going to say that this first row, first column should equal to B1, and that gives you the first equation. Second row, first column should equal to B2. That gives you the second equation. So that's interesting. It is possible to write these systems in the form of matrix multiplication. Now, in general, this is how we're going to write the system. The system is going to be A, and this is what A is. Matrix A is the matrix of only the coefficients, no variables. And then that multiplies by a column matrix of X, right? Capital, remember capital letters means matrices. So matrix A multiplied by matrix X. This is matrix X. And that equals to matrix B. This is the matrix form of the system. Everyone okay on that one? And then we'll show you how to solve this. And the way to solve this, by the way, is to do Gauss-Jordan on the augmented matrix. So what we do is, I'll show you in a moment, to solve this, we write the whole thing as a matrix that has 2 rows, 1, 2, 3 columns, and do Gauss-Jordan. Kind of like the starting problem that we did from previous section. That's how we're going to do it. So everybody okay on this work? All right.
Isn't it like very similar to the previous things that we were doing?
Yeah, exactly. Exactly. Very similar. The idea again here is to be able to write system in the form AX equal B. Now later, we want to see how do we solve for X. That's something we don't know yet, because these are all matrices, right? Remember, matrix division is undefined. So I cannot say X is B over A. Remember, these are matrices. Matrix division, undefined. So the question is, how do I solve for X, the matrix of variables? And we'll answer that later on. Okay, so are we good on this work, everybody?
Yeah.
All right, fantastic. Now, let's see. Okay.
Just one question. We do split it like that, right? The matrices, how you did it.
Right. We do write them, and we'll see later. We will write them as this in the form of product of 2 matrices equal to another matrix. The thing we don't know right now is how do I solve for X? Because this is a matrix. Again, I'm not allowed to divide by A because this is a matrix. You cannot divide matrices, and this is a matrix. So that's kind of where we're going with this. We would like to finish this using matrices, but we don't know quite yet how to do it. Okay. Now, is everyone okay on this one? All right, let's move on. Now, there is a consistency theorem for linear systems. Okay. And let's talk about this one. I'm just going to write it as that. Consistency theorem of, or instead of, sorry, let's say for linear systems. That's what we're doing primarily in this course, linear systems. Means each equation is going to be a first degree equation. Okay. Now, the form of AX. Now remember, folks, remember matrix matrix X. Isn't this matrix X from previous page? We can think of a column matrix as a column vector, couldn't we? So if you want, we can write it as X and arrow on top. If I do that, I can rewrite, instead of a capital X, I can write a vector, a column vector of variables x equals to b. Again, capital B. Wasn't that B1, B2 on the previous page? Now I choose to see it as a column vector. So it is possible to also write the system like this. Now, the consistency theorem says that this system is consistent. Let me write it. This system here is consistent if and only if that matrix B or vector, column vector B can be written as a linear combination. And what linear combination we're talking about? This is a linear combination. AX you should be able to write it as x1 a1 plus x2 a2 and so forth plus xn an equals b. Now, what do these a's, by the way, look like? So, for example, a1 here, this is what a1 looks like. A1 is going to be a column vector of just the coefficients on x. See, A1 goes with x1. So it's going to be a column vector, A11. First row, first column. Second row, first column. Third, fourth, and so on. Mth row, first column. So that's what A1 is. A2 should be a column vector. A2 is going to be what? For this one, is going to be in the first row, second column, right? 1, 2. Second row, second column. Mth row, second column. And so on and so forth. What does A sub n looks like? That column vector is going to be first row, nth column, second row, nth column, and so forth, all the way to the mth row, nth column. So if we can write, again, this system as a linear combination of these, then it is consistent. And remember, consistent means it has a solution. That's what that means. When we say the system is consistent, let me write that. Consistent systems have at least one solution. So that's what consistent means, sorry. Consistent systems have at least one solution. Okay. Everyone good on this one? Now,
can you explain again if, like, are you saying, like, if all of them are matching each other in the sense of the same rows and the same columns?
Right. Remember, sure. Remember the matrix we said is in the form, the general form. In the beginning, this is what we started with. First row, first column. First row, second. First, third, first, n. And then we have second row, first, second, 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 third, second, and n. And all the way to M1, mth row, second column, mth row, third column, and we have mth row, nth column. Remember, that was the form of that matrix A, right? So all we're doing here is this. And the matrix X look like this. It's going to be X1, X2, X3, X sub n, right? That's our matrix of variables. So all we're saying is that we can actually partition this matrix into column vectors. So this is a column vector, that's this one, A1. This is the column vector, second column, so it's A2. Third column vector, 3. Nth column vector, like that. So we can actually rethink the system as a combination of this A11, 21, and so on, multiplied by x1s. So what does by x1, x2, x3? So let's multiply ax, and you'll see what this will look like. I'm going to multiply first row, first column. So it's going to be A11, x1, A12, x2, A13, x3. You see how they multiply? Plus A1n, xn. And that should equal to matrix B, this matrix B. What does B look like? B is made up of the constants. So B is like B1, B2, B3, Bn. So all of this, first row times first column, that product should be, that's going to be B1, isn't it? This one, just the first row, first column should be B1. And then we do the same thing with the second row. So the second row is A21 times x1 plus A22 x2. And so on. AM2, or let's see, we're doing rows by, yeah, A2n. See, I'm doing A21 by that, A22 by this, A23 by this, A2n by xn. All of these should add up to B2. And then you do this for all of them. This would be 2, 3, x3, just to keep the pattern. And then all the way up to the last one. The last equation is AM1 times x1 plus AM2 times x2, and so on. Last one is AMN times xn. That should equal to Bn. So that's what all of this is telling us. Once you put them back together as a matrix, it makes sense, that multiplication. So this linear combination, remember, what it does, it partitions the matrix. This is the matrix. It partitions it into column vectors. See, column 1, column 2, column 3. Each of these themselves is a matrix there. It's a column matrix, column, 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 all the way to the last one, a column matrix. So that's what this will do. This linear combination, we will use this later on. You will see, in order to show, for example, the system is consistent, we're going to say, well, let's see, am I able to do this or not? And then once we use numbers, it's going to be easier with numbers, I promise you. This is just with notations, so it's kind of cryptic. Are we okay on this, everybody? Now, we're done with this section. I know we reached our break here. It's 7:35. So if it's okay with everyone, then I'm gonna stop recording here and or pause it, stop share, and then I'm going to, where is recording? There you go. I'm gonna pause. Okay. So again, before we get started, any questions, anyone, about the things we've done so far this evening? Which is basically, we determined operation on matrices. We learned how to add, subtract, and multiply them pretty much. And then we learned that it is possible to show a matrix, a system of equations in the form of matrices. So that's what we've done so far. And then we'll actually solve some exercises here momentarily. So let me go to the book, and that's the one I'm sharing, and check out this example 7. In example 7, what I'm doing here, or not what I'm doing, what I'm showing here is this last thing that we did, the very last thing we did, that was the consistency theorem that said a matrix or a system is consistent if it can be written as a linear combination of column vectors and the vector of unknowns, the x1, x2, and so forth. So I just want to show you the example that's in the book of that. So here you have a system, 3 equations, 3 unknowns. Now notice that the system can be written in matrix form. So that's what we're talking about here. And here's x1, and this would be a sub 1. See the column vector 1, 4, 7. Those are the coefficients in front of x sub 1 plus x sub 2 times the column vector 2, 5, 8 plus x sub 3 column vector 3, 6, 9. So again, all that is just a notation for the matrix. Okay, we can do it that way. Now, and then it says using Gauss-Jordan, you can show, we'll do that in the exercises ourselves. It says you can show that this is the solution to the system, what they show here, and they plug it in, and then they show you that, look, it is possible for this to work. If you do 1 times 1, 4, 7, 1 times 2, 5, 8, negative 1 times 3, 6, 9. So you're going to do 1 plus 2 minus 3. That's 0. 4 plus 5 minus 6. That's going to be 3. 7 plus 8 minus 9. That's 6. So they just want to show you that the solutions they have here works. The left side equals the right side. So just this is what we meant by writing a system as a linear combination of column vectors and the variables x1, x2, x3. So I just wanted to clarify that one. Now, let's actually take a look at some of these exercises. And for instance, looking at number 16, let me go to number 16. I'm going to write it down, and then we'll work this together. So we are in section 2.1, and this is exercise number 16. In number 16, it says solve for x, y, z, and w. So we have w, x, y, and this is actually x. There's, notice in number 16, oh yeah, the z is on the other side. That's equal to -4, 3, 2, -1, plus twice y, w, z, and x. Okay, so we want to solve for the unknowns. Let me switch to my pad here, my notepad. Okay, and this is what we want to do. We want to solve this for the variables. Now, remember, this is also x, so we have 2 x's. The second column is just made up of x and x. Now, in order for this to work, remember, 2 matrices are equal if every element in the same position in the matrices are the same or equal. So I'm going to first combine the right side. On the right side, it's -4 plus 2y. So this is -4 plus 2y. First row, second column, 3. First row, second column, 3 plus 2w. Correct? And then second row, first column is 2 plus 2z. And finally, second row, second column. That's -1 plus 2x. -1 plus 2x. So those are the elements of the sum vector, this or sum matrix. On the left side, haven't done anything, so we have W, X, Y, X, right? Now, again, for these two matrices to be equal, like elements must be the same. So in other words, W is -4 plus 2y. Okay, so I'm just going to write these now. W has to equal -4 plus 2y. How about X? First row, second column. X should be 3 plus 2W. And what else? And then the Y here, second row, first column. Y must be 2Z plus 2, right? 2 plus 2Z. And finally, second row, second column, X is -1 plus 2X. Right? So pretty much this is what we have, matching the elements, like elements together. So let's see. We should be able to solve this, right? And here, from this equation, I can isolate X, subtract X from both sides, add 1 to both sides. So this will give me X is 1. True. Subtract X, I have X here. Add 1 to both sides. So that's X is 1. Now, once X is 1, I can back substitute into this equation, right? In this equation, the left side is X, but then X is 1. The right side is 3 plus 2W. Now I can solve for W. Subtract 3 and divide by 2. So W is -1. Good. So we solve for X and W. Now, once I solve for W, I can look at this first equation. And in there, I can solve for Y now. Remember, W is -1. Plug it into this equation. So now I have -1 is equal to -4 plus 2y. And then we can isolate the y. Add 4 to both sides, so I get 3 equals 2y. And that means y must be, what, 3/2? And we have that one. So we solve for x, w, y. Now I can solve for z because we solve for y. So from this equation, y equals 2 plus 2z. That's 2 plus 2z. And now we can solve for z. For this one, subtract 2 from both sides. Subtract 2. -2 plus 3/2 is -1/2. And divide both sides by 2 or multiply by 1/2. That isolates the z, right? Multiply by 1/2 by 1/2. Z turns out to be -1/4. And there we have it. So that's how you would do number 16. Is everyone okay on that one? We're good. Number 16. If you're good, let's take a look at another one. Again, no questions on number 16. All right, if no questions, let's take a look at another exercise. Share the book. All right. And I'm keeping an eye on the way by on the exercises that you will be doing for the homework. So I'm trying to do something similar to those. Let's take a look at number 40, for instance. Now this book has a lot of exercises, but these exercises that I'm skipping over. So for instance, check this out, folks. For number 18, 17, 18, and so on, 17 through 30. It just says multiply, A, B, B, A, B, B, A, like that. So you can try these and see how it turns out. Let's go to number 40. In exercise number 40, there you have that one. The question reads in number 40, solve the matrix equation. So I'm going to write this down again on my paper. So this is exercise number 40. Matrix AX equals 0. All right. So matrix A is going to be a 3 by 4. That's going to be 1, 1, 0, 2, negative 1, 1, 1, 0, negative 1, and 3, 1, 2. Matrix of variables x is going to be x1, x2, x3, and x4. And note, by the way, how the author is not using boldface on A, right? It is a matrix, but we don't use boldface for the matrix. And notice he's using a boldface for X, isn't he? So he's thinking, remember, a column, a vector, and a column matrix are the same thing. So he's thinking X here as a vector. Okay. In other words, I'll show you my paper in a moment. AX. And look at 0, for example. You see 0? It is a matrix, but he chooses to think of 0 as a 0 vector, a 3 by 1 0 vector. So I'm writing it on my paper. I'll show you in just a moment what I'm writing here. All right, so that's what he's thinking. Now, he says solve the matrix. So that's what we're going to do in just a moment. Let me change my share to my notepad. All right. And this is what I was writing down, jotted down as I was reading the problem. You see here, I'm using the vector notation instead of matrix notation. Why? Because he's thinking of a matrix, so I have a matrix. And here, he used boldface. Remember, boldface in this book means vector expression. So that's a vector. It's perfectly fine if he didn't use a vector. He just used capital X. Look at the 0 vector. This is a vector or a matrix. He chooses to call it a vector of 0. A 3 by 1 vector of zeros. Right? So that's what that is. Now we want to solve this, right? We want to solve this system. Now, so let's go to, we're going to go to Symbol Lab and do this, okay? But before we do, I need to write the augmented matrix. Remember, the augmented matrix is the matrix of coefficients, the A coefficients, and then you attach the matrix of constants to it. That's, you augment it, you annex it by the zeros. Okay, so what is this going to look like? My matrix is going to have 3 rows, 1, 2, 3, 1, 2, 3, 4, 5 columns. Okay, so the row is 1, 2, 1, 3, bring the 0 in front of it. See, we just augmented it. And then we have the second row of A. I'm just copy, pasting it. 1, negative 1, 0, 1, attach another 0. And finally, the last row is 0, 1, negative 1, 2, 0. And there you have it. And this is what we call the augmented matrix. Now, what we're going to do next is we're going to go to Symbol Lab. Remember, this is the matrix I'm going to turn into Symbol Lab. So let's do that. Let me stop this share and share. There's Symbol Lab. Share this one. Okay. And again, please, if you don't see something I'm calling out, just tell me, your Symbol Lab is not showing. All right. Now, we have a matrix. I'm going to copy from my paper. I had a matrix, 3 rows, 5 columns, right? A 3 by 5, and I don't see a 3 by 5 here, but no big deal. Let's backspace, and we create our own 3 by 5. So what is this 3 by 5 going to look like? I'm going to go here. Remember, as you do this up here, it shows you the size of the matrix. So I don't have to actually go 1, 2, 3 like that. Just go until what you want. Up here, I'm reading the numbers. I want a 3 by 5. That's 2 by 6. It reads 3 by 5. And I left click once. Now, we're going to type in the numbers. 1, right arrow, 2, right arrow, 1, 3, 0. The second row is going to be 1, -1, 0, 1, 0. And the last row is 0, 1, -1, 2, 0. Give you a moment to catch up if you're following along with me. So there you go. And we want to do a Gauss-Jordan of this. Okay. And go. And here's the solution, the Gauss-Jordan. See that nice column? I'm sorry, the diagonal of ones? Okay, perfect. So now I'm going to write this on my paper. Okay, so this is now the Gauss-Jordan form. It's going to be 1, 0, 0. Now imagine, folks, if you had to do this by hand, it's just going to take a long time. And again, it's really not necessary. That's just a lot of busy work that goes nowhere. Why torture ourselves, right? So there you go. That's going to be the Gauss-Jordan. Now, our task is to read the solution. We did this last week, reading the solution from Gauss-Jordan form. So anyone want to chime in? What does this last row reads? Remember, the coefficients are x, first column, x sub 1, x sub 2, x sub 3, x sub 4, and then each of those equations equal to 0. So what do you think the third row is telling us?
C equals -1.
Okay, let's see. 0x sub 1, 0x sub 2, 1x3, isn't it? Again, I'm going to write this on the paper and then I'll show you. 1x sub 3, and then isn't it negative x sub 4, right? Negative 1x sub 4. And that should equal 0, shouldn't it? Okay, and I have the matrix now. Let me go back to my notepad here now. Stop share and change my share to that one. Okay. So here I wrote this matrix, copied it from Symbolab. So this is the matrix that I have. This one. Isn't this what the third row reads? 0x1, 0x2, x3 minus x4 is 0. And remember, for this one, we talked about free variables. Which of these two variables is the free variable? Would it be x sub 3 or x sub 4?
X sub 4.
Good, x sub 4. So we're going to let x sub 4 be t. And by the way, if you look at this system, we have 1, 2, 3 equations, 1, 2, 3, 4 unknowns, right? x1, 2, 3, 4. So anytime you have more variable than equations, the solution has to be parametric. So that's why we're declaring x sub 4 to be t. So that's our free variable. Once x sub 4 is t, can I solve for x sub 3? Right, move this over. and replace x sub 4 with t. This is our free variable. So that's going to be t. Therefore, x sub 3 is t also. Okay. Now, what about x sub 2? What does the second row read? An equation for the second row. It would be 1x sub 2, right? So that's just the second row. Says or reads x sub 2, 0x sub 3 plus x sub 4 equal to 0, right? But then we said x sub 4 is our free variable. So from this, x sub 2 is going to be negative x sub 4. And that means negative of t. And that's the third unknown. And now we can solve for x sub 1 from the first equation, right? 1x1, 0, 0, 2x sub 4. So that's x sub 1 plus 2x sub 4 equals 0. Therefore, x sub 1 is move x sub 4 to the other side. It's going to be negative 2x sub 4 or negative 2t. And we have solved the system. Again, parametrically, we don't have a unique solution here, folks. We have infinitely many solutions. If you choose to let, for example, this is a solution that works. Let t be 0. So I don't have to use a calculator. It makes it easy. When t is 0, I have 0, 0, 0, 0, right? So all the x's are zeros. Correct? This is called the trivial solution. Anytime you have a system that's equal to 0, this is called a homogeneous system because you have zeros on the right side. Then the solution, make all variables, each and every one of them 0, and it works. So that every one of them has trivial solution. What if I want non-trivial solution? Let t be 1. Now, if t is 1, look at x sub 1. Negative 2t, that's negative 2. X sub 2 is negative t. X sub 3 is t. And x sub 4 is t. You see that? This is one of infinite number of solutions. And this one, we're going to call this one non-trivial solution. And we are always interested in the non-trivial. Who cares? If 0, 0, 0 always works, then what's the big deal of that, right? We want non-trivial. And there's going to be infinitely many of those. If you want, let t be 5. So we get whatever this, and that's another solution. Okay, so everyone, are we good on this example, exercise number 40? We are good. If we are okay on this one, let's take a look at maybe one more. Let's take a look at number, go stop share. And we're going to go back to the book. How about, let's check this one out. How about number, I don't know, is 52 okay? 52 is this one. There, number 52. In exercise number 52, and let me grab my paper. So we're in section 2.1. And we're about to do number 52. So in number 52, the question says, write the column matrix B as a linear combination of the columns of A. The column matrix B. Okay, number 52, so that's B. We want to rewrite this one as linear combination of columns of A. Remember AX equal B. That's what we want to do. And so let me copy this matrix first. Matrix A, -3, 3, 4, 5, 4, -8. And then B, the vector, column vector B is -22, 4, 32. All right. So let's do this. Again, the question, let me change my share to my notepad. All right, so this is what I just did. I rewrote what was on that page. I wrote it on my paper. Now, what we want to do with this one is the following. We said AX is equal to B, right? And what was AX? AX is, remember, these are columns of A. So AX means X1 times A1, which is -3, 3, 4, right? And plus X2 times the second column of A. That's going to be 5, 4, and -8. And that's going to equal to matrix B. So that's what we mean by linear combination, folks. -22, 4, 32. Okay. So hopefully everyone is good. Now we just have to determine X1 and X2. And then we can write it, and then you'll see exactly what this looks like. So to solve or to find X1, X2, I need to solve the system, right? So let's write the augmented matrix. And what will the augmented matrix, by the way, look like, folks? This augmented matrix. Remember, it's going to have all the elements of A in it, right? So it's going to be -3, 3, 4, 5, 4, -8. So it's going to have that. And then we're going to augment it with constants, the B's. And that's going to be -22, 4, and 32. That's what we call the augmented matrix. And then what do you think we got to do next? Once we have the augmented matrix, next step would be to do what?
I think you'd want to find the I think at least going from the last example, maybe find the Gauss-Jordan of it, or like do something with the x's.
Very good. We got to do Gauss-Jordan. Remember, Gauss-Jordan's actually, we're going to solve it next step. The Gauss-Jordan solves it. So thank you. That's actually correct. So let's do Gauss-Jordan, and I'm going to go to Symbol Lab to do it. But before I do, I'm going to prep this. Let me go to Symbol Lab, and then we'll talk again. Stop share, and let's go to Symbol Lab. Okay. In Symbol Lab, we're going to, there you have Gauss-Jordan. So I need to do, in this, our matrix, it has 3 rows and 3 columns, right? So there you go. There's a 3 by 3 already up there. And I'm just copying the numbers, -3, 5, -22. And then we're going to go 3, 4, 4, and 4, -8, and 32. So please check, make sure I did it right. I think those numbers look good. And then Gauss-Jordan. Go, and there is your Gauss-Jordan right up here. So I'm copying the numbers now. 1, 0, 0. And then I have 0, 1, 0. And then 4, -2, 0. Okay. So clearly this last equation is not useful, is it? Right? Remember, by the way, how many unknowns we had in this exercise?
Two.
We had 2 exactly, didn't we? X sub 1, X sub 2. So look here, we have 1, 2, 3 equations, 2 unknowns. So 1 equation is too many, isn't it? We just need 2 of them. And that's what this row of zeros tell me. It just says one of these equations, this one, this one, this one. In fact, you can choose any one of them. Any one of these equations could be rewritten as a linear combination of the other 2. So for example, I can rewrite the first one. If I try, I could rewrite it as the sum of row 2, row 3. Not just add them, but the constant multiple. So that's what this tells me. Now, what does the second row of this matrix tell us, by the way?
Would it be x of 2 equals -2?
Perfect. Thank you. Now let me switch back to my notepad. Thank you for that. That's exactly what it means. So the second row, remember, these are the coefficients on x sub 1, x sub 2. So this says x sub 2 is -2. But there, we solved it. And x sub 1 is 4. Right? So we found those. Now, we can answer the question. The question says, show that B can be written as a linear combination of columns of A. B, which is the matrix, -22, 4, 32, can be rewritten as x sub 1, A1, plus x sub 2, A2. Now, what is x sub 1? X sub 1 is 4, so that means 4 times. What is column vector A1? That's just the vector of these coefficients, -3, 3, 4. Plus x sub 2 is -2, parentheses, -2 times a sub 2, vector a sub 2 is a column vector A2. That's going to be 5, 4, -8. So that's what that linear combination earlier we talked about, that's what this means. And you can see that it works again. 4 times -3 is -12, plus -10. -10, -12 is -22, you see? So all of those numbers are going to work. Now, are we okay on this exercise, everyone? Yep, we're good.
Yeah.
All right, thank you, appreciate it. Perfect. So now if we're good on this one, so we're done with this section. Let's actually go to our section 2 now. Let's take a look at section 2. I'm going to go to the book here. In section 2 of the book, there you go. So now we're going to look at just some of the properties of matrix operations. Now these properties are there. Instead of me writing them, if that's okay, I just go over them on the screen with you so we can do more exercises together. So in section 2, we want to look at properties of matrix operations. Now, this is our first theorem. The first theorem says, remember now, A, B, C, these are matrices, m by n. Every one of them has the same size. Little c and little d are scalars, means constants. So, property number 1. That's the commutative property, right? A plus B equal B plus A. We already showed that. We worked on that. And property number 2 is the associative property of addition, just like with numbers. You can change the grouping. Doesn't matter if you add B and C, add the result to A. Or do A plus B, add that result to C. It works. Scalar multiplication, CD times A would be C times DA. This is again associative of multiplication. Remember, with associative property of anything, you change the grouping. So instead of CD grouped together, we're going to group D times A, then multiply C times that. This one, the multiplicative identity, scalar 1. Remember that 1 is a scalar, not a vector. Scalar 1. 1 times any matrix gives you the matrix. The next one is distributive property of a scalar, C. C times the sum of two matrices. If you want, you can distribute C to A, distribute C to B, and then add them. And finally, the distributive property of this time the matrix to the real numbers, the constants. You do C times A, dA. So again, these are all, they behave, they work like you would expect them to. Are we okay on the properties, everyone? And then the proofs are these if you're interested. Next thing we're going to look at is the zero matrix, by the way. A zero matrix is just that. It's the matrix that's made up all zeros. So this is a 2 by 3. See, first row columns. 2 rows, 3 columns. This is a 2 by 3 zero matrix. It's called the additive identity because any matrix plus the zero matrix gives you the matrix itself. Okay. And then we go to this theorem. This theorem, properties of now zero matrix. Any matrix added with a zero matrix gives you A itself. Remember the additive identity? Any matrix added with, think of this as its opposite, negative A. Any matrix added with its opposite give you the zero matrix. Now remember, we distinguish between zero matrix and scalar zero. So this is a matrix of zeros, means it looks just like it does up here. And finally, a constant multiple of A. If C is equal, if C times A gives you the zero matrix, two things could be true. Either the scalar is zero, because 0 times anything is 0. So that's what this says. Either the scalar is 0, the constant is 0, or A itself is a zero matrix. C could be anything else. If you have a matrix of all zeros, you multiply 5 times that. You're still going to get 5 times 0, 5 times 0, 5 times 0, like that. So hopefully everybody is okay on theorem 2.2. We're good. All right, let's go to theorem 2.3. No, theorem 2.3, we're looking at matrix multiplication. Okay, how does it work with matrix multiplication? So we're multiplying A, B, C, right? And the assumption here is this. It says with sizes such that the matrix products are defined. So suppose the inside numbers are equal and all of that stuff. If we can do the product, you can do product of A, B, C. You can change the order of product. Instead of B, C, we can do A times B and then multiply that times C. Again, the associative property. Associative changes the grouping. Next one is the distributive property. Matrix A times B plus C. You do A times B plus AC. That's good. Works just like the numbers. This one is like distributive property from the right. So you go AC, BC. There. You got to be careful here, though. For example, see, A plus B times C is AC. You cannot say that's CA. You see that even though you distribute from the right, we cannot say CA because AC will be defined, but CA may not even be defined. So we got to keep the order in that. Number 4, a constant multiple, scalar, times AB. You can multiply the constant by A if you choose to. There, this one. And then multiply that by B, or if you like, make the constant reach all the way to B, this one. And then multiply A by the result of that. Are we okay on the properties of matrix multiplication, everyone? Okay. And let's see. The non-commutative property, we already mentioned that. Remember, we said AB doesn't equal BA. He's just illustrating the same thing. So
Yeah.
we already talked about that one. Is everyone good on this one?
Yeah, we are.
Okay.
We remember
Yeah.
that it's because of the columns and the rows that if sometimes they may vary, so therefore it doesn't work.
You got it. Thank you, Jesus. Exactly. Exactly. Now, for this particular one that he's doing, both of these are 2 by 2, 2 by 2. So A by B would be 2 by 2. B by A would be 2 by 2. So it's actually defined, right? BA is defined. He did it. This is the matrix. AB is defined, and he did that. This is the matrix, but look at the results. 2, 5, 4, -4, 0, 7, 4, -2. They're not the same. So even if the multiplication is defined, commutative property of multiplication does not hold. Okay.
Does that mean that there's two different solutions? If each one is defined differently?
Right. And remember now, we just simply are multiplying, right? Multiplying. So right now, we're not looking at the solution, but you're right. Later on, we'll see this and I'll emphasize, keep this in mind, AB doesn't equal BA. So when we go try to solve for X in that XA equals B, I got to be careful how I multiply the matrices to isolate X. So I'll point this out again. If I forget, please remind me. But for now, we just want to say, look at AC. AC is this, right? Look at, what else? Oh, this is cancellation going back to here. So for now, just remember, matrix multiplication is not commutative. A, B, B, A, they're not the same. Now, here's an example. He's showing what we usually do in algebra. In algebra, suppose A, B, C, these are numbers. In algebra, it's perfectly fine to divide both sides by C, isn't it? But that's in algebra and with numbers, not with matrices. We cannot cancel the C's here. You see that? So he's saying cancellation is invalid. So we just got to be careful how we handle these products and the equations. So we cannot cancel, and product is not commutative. Now, let's look at the identity matrix. This is an identity matrix of order n. And look at, by the way, how they write it. See that? Just subscript n. They don't put it as n by n, right? As a matrix. So let's assume or let's agree. When he does I sub n, it really means I n by n. Look at I sub 2. I down here. I sub 2, that's a 2 by 2 matrix. There it is, 2 by 2. The identity matrix always has a diagonal elements that are 1. Every one of the diagonal elements must be 1 and 0 elsewhere. So when you look at this, for example, this matrix I3, does this kind of ring a bell? Have you seen something like this before?
Yeah.
Exactly. Very good. Thank you, Angel. This is the Gauss-Jordan form, isn't it? So the identity matrices are all in Gauss-Jordan form, all of them. Every one of the identity matrices are. Okay, and there you have that one. Now, what are the properties of the identity matrix? The identity matrix is like multiplicative inverse. You know, any number times 1 is itself, right? 5 times 1 is 5. So this time, this would be the multiplicative inverse IN. So any matrix A that times by the identity matrix will give you A. It doesn't matter where you do A times I, and check this one out. I times M. See that? So whether you do post means after, whether you do post multiplication by I or you do pre-multiplication by I, the result is always A. Okay. And he's showing you here a couple of examples. So here's a matrix A. This is identity matrix of order 2. When he multiplies it, look what happened. He gets exactly the original matrix back. See? He gets A back. So he's doing number 1 here. A times I is A. Look at this one now. He's doing number 2 with part B. He's multiplying an identity matrix times matrix A, this matrix. The result is matrix A. Isn't that cool? So again, whether you post or pre-multiply by I, the answer is always going to be the matrix A. We're good on that one. Now, let's take a look at, like, for example, can I square a matrix? Sure. To square a matrix, you multiply A times A. Right in here, you multiply A by A. If I want to cube a matrix, that would be AAA. You can raise a matrix to the 4th power. That would be AAAA, multiply by itself 4 times. So in general, you can raise a matrix to the kth power. That means you have to multiply by itself k times. So that would be, again, raising matrices to a power. It is doable. Now, notice just like with numbers, remember, anything to 0 other than 0 is 1. This one, any matrix to the 0 power gives you the identity matrix. Oh, these identity matrices, by the way, let me go back up, sorry. There you go. If you look at these initially, they're all of them must be square matrices. So this is n by n. I2, that's a 2 by 2 is square. This is a square. Identity 1, that's a square, right? 1 by 1, 2 by 2, 3 by 3, 4 by 4. So remember, identity matrices are never 2 by 3s, 5 by 4s. They're all square matrices. Okay. And almost done with this, folks, with this section 2.2. Now for this one, theorem 2.5. This one looks at the number of solutions for a linear system. So any one of these 3 things could happen when we solve a linear system. We either have a unique solution, which is what we like, or we have infinitely many solutions, or no solution. So that's what this theorem guarantees. 1, none, or many. That's what could happen when we solve a system, linear system of equations. Okay, on that one. Next idea is the transpose of a matrix. So here's matrix A. The transpose of that matrix is when you turn the row, look at the first row here, highlighted in pink. When you turn that first row, rotate it 90 degrees clockwise, and you get this column vector now, right? So the row, first row becomes first column. That's what transposing does. Look at the second row. Second row, rotated 90 degrees clockwise.
What's the
Now,
purpose of that?
pardon?
What's the purpose of
Oh, the
turning them?
purpose of transpose?
Yeah.
You'll see these as we go through. We can use properties of transpose sometimes to solve systems. Or we can use them to prove other theorems. So that's the idea of transposing them.
All right. Sounds
Yeah,
good.
we'll see. I promise you, you'll see that.
Yeah, just backtracking a little bit. Anything more than one solution means many solutions?
Exactly. Oh, a linear system has either exactly one or infinitely many. So it's not going to have two solutions. It's not going to have
Oh,
three.
okay.
It's either one or infinite. In other words, the system is either consistent, has exactly one, or a dependent system that has infinitely many. Good point on that. A linear system will never have 5 solutions, never have 6 solutions. It's either one or infinitely many. There is no in between. And of course, there is a case where it may not have any solutions at all. All right, now the transpose. So here we have a transpose of row 1, rotate 90 degrees. So the rows become columns. Keep that in mind when you transpose it. Look at the examples, are easier to see. So for instance, look at A, it's a 2 by 1. 2 rows, 1 column. When you transpose, you actually change the order of rows and columns, right? So 2 rows, 1 column becomes 1 row, 2 columns. There you go. Again, just to rotate this 90 degrees, this column becomes a row. Look at B now. This one, matrix B. Matrix B, transpose of B. So the row 1, 2, 3 becomes column 1, 2, 3. Row 4, 5, 6 becomes column 4, 5, 6. 7, 8, 9, third row becomes 7, 8, 9, third column. You see how that turns? So these are all transposes. Now, here's the property of transpose now. The properties of transpose, suppose we have A and B are matrices such that the operations are defined. When you do transpose of a transpose, you get the matrix back. So it's like turn the row into column and then turn it back, the column into a row. That's what this does. So transpose of a transpose gives you the original matrix. A plus B, transpose of the sum is sum of the transpose. A constant multiple of A transpose, the transpose only takes effect on A. That's a scalar, so it doesn't do anything, right? So that's often called transpose of a scalar multiple. So be careful. Do not do transpose on the constant. Just ignore it. It doesn't participate. And number 4, this one we'll use later. A times B transpose. It is not A transpose, B transpose. See number 2, A plus B transpose. Isn't that A transpose, B transpose, sum? It doesn't work for the product. AB transpose is not A transpose, B transpose. You actually change the order of transposition. So it becomes B transpose times A transpose. Remember? So if you have a product transpose of a product, you change the order of the product with transpose. And there we have those. Are we good on these, everyone? All right. And You kind of see here in this example, transpose of a product. So here he has A and B. The product AB is this right in here. That's AB. Now, AB transpose, remember, a row 2, 1 becomes column 2, 1. Row 6, -1 becomes column 6, -1. That's AB transpose. Now, and remember the property we had up here? We said AB transpose is B transpose A transpose. He's going to verify that. Here's AB transpose. Look at B transpose, A transpose. So this is B transpose, right? Remember that was B, change the rows into columns. A transpose, change the rows into columns. Then multiply them and look at that. ABT looks exactly the same as BTA. So it works there. And that's just the validation of what we just saw. And he again recalls it. This is important. The order of transpose changes. All right. So the little time we have left, about 10 minutes. I know you guys are getting tired. It's late at night. So let's take a look at some exercises here. Okay. First of all, any questions? Is everyone doing okay? Yeah, okay, thank you.
Well.
All righty. Again, I won't hold you much longer. I know it's getting late. So let's take a look at the exercises here. Now, in these exercises, let's see. The ones involving products, those you can do. A whole bunch of these. I think you're going to be okay on the first 6 problems, right? Exercises like these. You're adding 3 matrices, right? Number 1. So you're just going to add each component, like -5 here, adds with 7, adds with -10. So those are just basic addition. Let's do something that may be more interesting to you. Let's do something with maybe the transpose. Again, all of these folks, you can try them. If you have trouble next week, I'll be happy to work them. You just literally have to just multiply these out. A whole bunch of these are just add, multiply. Add C plus C, multiply CB times. So just try these and see how that works out. Let's see. How about, I think we're doing number 41. Let's take a look at number 42 here. In number 42, it says verify AB transpose is B transpose A transpose. Okay. So I'm going to go ahead and write this one. This is section 2.2. And we're doing number 42. So I'm just writing the matrix A, 2, 0, 4, 1, 1, 0, -1, 3, 2. Matrix B is 1, 2, 0, 0, 1, 1, -1, -2, and 3. Oh, and by the way, folks, Symbolab may be able to, I haven't tried it yet, may be able to do product. I don't know if any of you've tried it. So try it if it does. If not, in our Canvas, I have a couple of other links to websites where you can actually multiply matrices to make it go faster. So just want to point that out. Let me change my share to my notepad again. All right. So here I have the 2 matrices A and B. This is exercise number 42. So we want to verify AB transpose. So let's AB, multiply AB. Now matrix AB, and again, you're welcome to verify this by hand or use your TIs or use the links on Canvas shell where I have two other sites that you can multiply matrices. Honestly, I use those sites. I didn't do this by hand. So that's how I got this product. Now, the transpose of this, what will the transpose of this be? Remember, the transpose is when you turn the rows into columns, right? First row becomes first column. So we're just going to write 4, 0, negative 7. Correct?
Yes.
The second row becomes second column. So that's going to be 2, 4, 7. And the third row becomes third column, 4, 2, 2. Okay, so that's AB transpose. Now, it says verify, that is B transpose times A transpose. You see how we changed the order of, again, transposition here? AB becomes B transpose A. Now, B transpose, this is B. So we're going to transpose this matrix. So B transpose is 1, 0, negative 1, 2, 1, negative 2, 0, 1, 3, 0, 1, 3. Right? Rows become columns. Rotate them. This is B transpose times what is A transpose. A is the first one. Again, first row becomes first column, second column, third column. So this is going to be 2, 1, negative 1, 0, 1, 3, and 4, 0, 2. And then I went to the website and I actually multiplied them, or you can do it the hard way, like we learned how to do today. But once I did this, I get 424, 042, negative 772. And you can clearly see that these are the same. So that's what he wanted. He said verify them, and we did. Okay. Is everybody doing okay? Are we good in this example?
Yes.
Exercise? Okay, perfect. So I'm going to stop the recording here. Let me see. More. Where is recording here? Right up here.